What if everything you see, the stars, the planets, even the air you breathe, isn't as solid or as certain as it seems? What if, at the very foundation of reality, the universe itself exists in a state of endless possibility, waiting to be pinned down by the act of observation? This isn't science fiction. It's the mind-bending truth of quantum superposition, a phenomenon so strange it challenges our very understanding of existence. Picture this: a single particle can be in multiple places at once, spinning in opposite directions simultaneously, defying the logic of everyday experience. Now imagine that principle scaled up to the birth of the cosmos itself. What if the universe began not as a single defined point but as a shimmering fog of probabilities, a cosmic quantum superposition waiting to collapse into the reality we know today? The idea that superposition could be woven into the fabric of the universe isn't just a wild guess, it's a frontier of modern cosmology, a key that might unlock the deepest mysteries of creation. Think about the Big Bang. We imagine it as a single explosive moment, but what if it was more like a cosmic roll of the dice, with trillions of potential outcomes flickering in and out of existence until one became real? Quantum superposition suggests that before time and space settled into what we recognize, the universe existed in a state of pure potential, a superposition of countless possible beginnings. Some theories even propose that remnants of that quantum haze still linger, hidden in the faint echoes of the cosmic microwave background or the strange behavior of distant galaxies. Today, we're diving into 30 of the most extraordinary theories about the universe's first quantum superposition, ideas that stretch from the origins of reality to the far future of cosmic evolution. We'll explore how superposition might explain the birth of black holes, the nature of dark matter, and even the possibility of parallel universes branching off from our own. Along the way, you'll meet brilliant minds who have dared to question the limits of physics, and you'll see how their theories could rewrite the story of everything. This isn't just about equations or abstract concepts, it's about peering into the deepest layers of existence, where the rules we take for granted break down and something far more mysterious takes their place. So buckle up. By the end of this journey, you might never look at the universe the same way again. The Big Bang wasn't just a single, definitive explosion. It might have been the ultimate quantum gamble. Picture the birth of the universe as a cosmic flicker, a fleeting imbalance in an otherwise silent void. According to this theory, reality itself began as a quantum fluctuation, a microscopic hiccup in the fabric of nothingness that ballooned into everything we know. Think of it like a bubble forming in a boiling pot of water, except instead of water, it's an invisible sea of energy, and instead of a bubble, it's an entire universe blinking into existence. Quantum field theory suggests that empty space isn't truly empty, it's a simmering ocean of potential, where particles pop in and out of existence too quickly to measure. Under the right conditions, one of these fleeting fluctuations could have been stretched and amplified by cosmic inflation, the rapid expansion of space itself in the earliest moments of time. Imagine blowing up a balloon with a microscopic scratch on its surface. As the balloon inflates, that tiny imperfection grows into a vast, complex landscape. In the same way, a subatomic blip in the quantum foam might have been stretched into galaxies, stars, and planets by the universe's explosive growth spurt. What's even wilder is that this primordial superposition could explain why the cosmos looks the way it does today. The universe isn't perfectly uniform. Clusters of galaxies weave through vast cosmic voids, a pattern that might trace back to those initial quantum ripples. Some scientists compare it to rolling a pair of dice at the beginning of time, with the outcome determining the distribution of matter across the entire cosmos. And just like a pair of dice can land in countless configurations, The early universe might have existed in a blur of possibilities before collapsing into the reality we observe. This idea doesn't just rewrite the story of the Big Bang, it blurs the line between nothing and everything. If the universe began as a quantum fluctuation, then existence itself might be the rarest of accidents, a statistical outlier in an infinite sea of nothingness. Or perhaps it's just one of many bubbles in a multiverse froth, each with its own unique roll of the quantum dice. Either way, it's a humbling thought. Everything you've ever known, from the dust on your bookshelf to the farthest quasar, could trace its roots back to a single, unpredictable twitch in the void. But what if our universe wasn't born in isolation? What if the quantum superposition we see today is actually the cosmic aftermath of a spectacular collision between parallel realities? This is the multiverse collision hypothesis, an idea so radical it turns the concept of a single, solitary Big Bang on its head. Picture two bubbles in an infinite foam of universes, drifting closer until they touch. At that moment of contact, their quantum states entangle, sending shockwaves through both realities. Our universe might not have emerged from nothingness, but from the explosive merger of worlds we can barely fathom. This theory offers a stunning explanation for one of quantum mechanics' biggest puzzles, decoherence. In the quantum realm, particles exist in multiple states at once, until they interact with their environment, forcing them to choose a single reality. But why does this happen? A multiverse collision could be the answer. When two universes brush against each other, their overlapping quantum fields might trigger a rapid collapse of possibilities, like a cosmic game of dominoes. The resulting energy could have seeded our universe's structure, imprinting the faint fingerprints of that ancient collision into the fabric of space itself. Some models suggest these collisions could leave detectable scars. Imagine cosmic bruises, anomalies in the microwave background radiation, or strange voids where galaxies refuse to form. Astronomers have already spotted mysterious cold spots in the sky, regions so inexplicably empty they defy conventional explanations. Could these be the battle scars of a multiverse crash? Others theorize that dark matter, the invisible glue holding galaxies together, might actually be remnants of that other universe, particles left behind like cosmic dust after a high-speed collision. The implications are staggering. If true, our universe isn't just one possibility among many, it's a hybrid, a mashup of realities that once danced too close. Every atom in your body, every star in the sky might carry echoes of that primordial encounter, and if collisions can happen once, they can happen again. Somewhere in the multiverse, another bubble might already be drifting toward us, carrying the potential to rewrite reality all over again. This isn't just about where we came from, it's a reminder that the universe is far stranger and far more connected than we ever dared to dream. What if our three-dimensional universe, with all its depth, texture, and vastness, is nothing more than an illusion? A cosmic mirage projected from a flat, two-dimensional surface like a movie playing on a screen. This isn't fantasy, it's the heart of the holographic principle, a theory so radical it reimagines the very fabric of reality as a quantum code etched onto the boundary of space itself. Imagine the universe as a DVD. At first glance, a DVD is just a shiny disc, flat and featureless. But encoded on its surface are all the layers of a blockbuster film, the explosions, the dialogue, even the trick of perspective that makes a flat image feel three-dimensional. In the same way, the holographic principle suggests that every star, every planet, even your own thoughts, might be nothing more than quantum information painted onto the edge of existence. This idea didn't come from nowhere. It emerged from the study of black holes, where physicists noticed something bizarre. The maximum amount of information a black hole can contain isn't determined by its volume, but by the surface area of its event horizon. It's like discovering that the contents of an entire library don't depend on how many books you can stuff inside, but on how much text you can scribble onto the covers. This revelation led to a staggering possibility. If a black hole's secrets lie on its surface, maybe the entire universe works the same way. Every event, every particle, every law of physics could be a hologram, a three-dimensional projection of data stored on a distant two-dimensional plane. The implications for quantum superposition are mind-blowing. If the universe is a hologram, then the strange ability of particles to exist in multiple states at once might not be happening inside space. It could be a shadow of something far deeper. Picture a pixel on your TV screen flickering between red and blue. The real decision isn't happening in the pixel itself, but in the unseen code controlling it. Similarly, the superposition we observe in quantum experiments might just be the surface-level effect of information being processed on the universe's ultimate hard drive. Some scientists even speculate that this could explain why quantum particles seem to know when they're being observed, because measurement isn't collapsing a wave in our world, but updating the data on the cosmic hard drive. Could we ever find proof? Strange as it sounds, there might already be clues. The holographic principle predicts that space should have a faint graininess at the tiniest scales, like the pixels on a screen. Some experiments hunting for this quantum fuzziness, like ultra-precise measurements of distant starlight, have found tantalizing anomalies. Others suggest that if the universe is a hologram, gravity might behave differently at extreme distances, a glitch in the cosmic projection. Whether these hints add up or not, one thing is certain: if the holographic principle is true, then reality isn't just stranger than we imagine, it's stranger than we can imagine. We're not just living in the universe, we might be living on it, like characters in a story written on the skin of the cosmos. Here's a paradox that will make you question your own existence. What if the universe's first quantum superposition didn't collapse into reality until someone or something observed it? This is the heart of the conscious observer hypothesis, a theory so controversial it places consciousness itself at the center of cosmic creation. Forget telescopes or particle accelerators, the most fundamental tool in shaping reality might be the human mind. At least, that's what luminaries like John von Neumann and Eugene Wigner dared to propose. Their interpretation of quantum mechanics suggests that the universe didn't snap into focus until a conscious observer looked at it, like a dreamer waking up to find their thoughts had built the world around them. The math behind this idea is as elegant as it is unsettling. In the quantum realm, particles exist as probability waves, ghostly clouds of maybes that only solidify into definite states when measured. But who or what counts as a measurer? A machine, a cat in a box, or does it take a mind truly aware of the result? Von Neumann and Wigner argued that consciousness is the ultimate linchpin, the one force that can cut through the fog of superposition and force reality to make up its mind. Picture flipping a coin in a pitch-black room. According to this theory, the coin isn't definitively heads or tails until someone turns on the light and sees it. Now scale that up to the birth of the cosmos. The Big Bang wasn't just a physical event. It might have been the universe's first moment of self-awareness, a cosmic aha that crystallized existence out of pure potential. Not everyone buys this idea. Critics point out a glaring problem. If consciousness is required to collapse quantum states, then who or what observed the universe into being before any life existed? Some propose wild answers like panpsychism, the view that even atoms have a flicker of awareness. Others suggest time might loop back on itself, with future observers somehow reaching backward to influence the past. Then there's the simulation hypothesis, which frames our entire reality as a quantum computer waiting for its user to hit render. But perhaps the most haunting possibility is that we're alone, that the universe spent billions of years in a hazy half-existence, adrift in uncertainty, until the first conscious creatures finally evolved to give it meaning. The debate rages on, but one thing is clear. If the conscious observer hypothesis is even partially true, it blurs the line between physics and philosophy. Are we merely passengers in a preordained universe, or active participants writing reality into existence with every thought? The implications stretch beyond cosmology into ethics, art, even the nature of free will. After all, if observation shapes reality, then what happens when 8 billion observers are all looking at the world differently? Maybe the universe isn't just a place we live in. Maybe it's a story we're telling together, one quantum decision at a time. Black holes aren't just cosmic vacuum cleaners, they might be the universe's original quantum engines. Picture a singularity, that infinitely dense point at a black hole's heart, not as a dead end but as a cosmic reset button. According to the black hole quantum bootstrap theory, the universe's first superposition didn't emerge from nothingness or a collision, but from the extreme quantum chaos inside a black hole's core. Imagine a tiny knot of spacetime so twisted by gravity that the usual rules of physics snap, unleashing a storm of quantum possibilities. In that storm, reality itself could have rebooted, birthing our cosmos from the ashes of a previous one. This idea stitches together two of physics' most elusive puzzles, quantum superposition and gravity. While quantum mechanics rules the subatomic world and gravity shapes the cosmos, the two refuse to play nice in equations. But inside a black hole's singularity, where gravity becomes infinite, something extraordinary might happen. Theories like loop quantum gravity suggest that spacetime isn't smooth and continuous but made of tiny, woven loops. Think of it as the universe's fabric fraying into threads at the smallest scales. When those threads tangle under extreme gravity, they could create a quantum bridge between realities, a portal where superposition becomes the default state. String theory paints an even wilder picture. If particles are really vibrating strings, then a black hole's crushing gravity might have stretched those strings into a cosmic symphony of overlapping states. Picture a guitar string tuned so tightly it hums every possible note at once. That's how the singularity could have existed in multiple configurations simultaneously. Some models suggest this quantum dissonance triggered a bounce, like a compressed spring recoiling, launching the Big Bang as the black hole's death throes. Evidence might already hide in plain sight. If our universe bootstrapped itself from a black hole's quantum chaos, it could explain why the cosmos leans toward disorder. Entropy, the universe's tendency toward messiness, might be inherited from the black hole's own scrambled information. Even the cosmic microwave background's faint irregularities could be echoes of that primordial quantum storm. And if black holes birth universes, then our own cosmos might be nested inside something greater, like a Russian doll of realities, each with its own black holes spawning new worlds ad infinitum. The implications are dizzying. Instead of a one-time Big Bang, the universe might recycle itself through black holes, each collapse sowing the seeds of a new cosmos. Your existence wouldn't just trace back to stardust, it might hinge on a quantum fluke inside a long-dead singularity, a twist of spacetime so violent it birthed everything. If true, black holes aren't tombs, they're cosmic wombs spinning the fabric of reality from the unraveled threads of the old. Imagine a universe that never stops inflating, a cosmic souffle expanding so fast that entire new worlds are constantly bubbling into existence. This is the wild promise of eternal inflation, a theory suggesting our universe might be just one random bubble in an endless froth of reality. Here's how it works. In the earliest moments after the Big Bang, space didn't just expand, it exploded outward at speeds beyond comprehension, stretching the fabric of reality like taffy. But according to eternal inflation, this expansion never truly stopped. Instead, most of the cosmos keeps stretching eternally, while tiny pockets like ours slow down just enough to form stable universes with their own laws of physics. Now here's where quantum superposition enters the picture. In this frenzied sea of inflation, every new bubble universe could emerge from a quantum fluctuation, a random twist in the fabric of spacetime that collapses into a cosmos. Picture a pot of water on the verge of boiling. Before bubbles form, tiny quantum jitters create unstable pockets of vapor. In eternal inflation, those jitters don't just make steam, they birth entire realities, each frozen into a unique state by the randomness of quantum mechanics. Some might have stars and planets like ours, while others could be filled with exotic particles or forces we can't even imagine. But there's a catch: the measure problem. If infinite bubble universes are constantly spawning, how do we calculate the probability of anything? Normally, probabilities add up to 100%, like rolling a six-sided die where each outcome has a fixed chance. But in an eternally inflating multiverse, the number of possible outcomes is literally infinite. Does that mean every conceivable universe must exist somewhere, or are some configurations more likely? Physicists still grapple with this, but one clue lies in quantum randomness. The way a bubble universe's properties freeze could depend on the same unpredictable quantum jumps that make particles behave so strangely in the lab. Think of it like a cosmic lottery. Every new bubble universe is a ticket with randomly assigned numbers: the strength of gravity, the number of dimensions, even the existence of time itself. Most tickets might be duds, producing empty or unstable universes that collapse instantly. But a rare few, like ours, hit the jackpot with just the right conditions for life. The eerie part: this means the quantum superposition of the early universe didn't just shape our reality. It's still happening right now, somewhere in the endless expanse, as new bubbles flicker into being with every passing moment. What's even stranger is that these bubble universes might not be entirely separate. Quantum entanglement could link them, like invisible threads connecting distant realities. Some theories suggest that when superposition collapses in one universe, it might send ripples through the multiverse, subtly influencing others. It's as if every cosmic bubble is whispering to its neighbors, exchanging secrets through the language of quantum mechanics. So where does that leave us? If eternal inflation is true, then our universe isn't just a one-time accident. It's a single frame in an infinite cosmic film, with new scenes constantly being written by the rules of quantum chance. The next time you look up at the night sky, remember, those stars might not just be lights in the darkness. They could be footprints left by a universe that's still expanding, still creating, and still dancing on the edge of infinite possibility. To understand the universe's first quantum superposition, we have to shrink down, way down, to a scale so tiny it defies imagination. Picture space-time not as the smooth, invisible fabric we take for granted, but as a seething, turbulent froth bubbling with violent energy. This is the Planck epoch, the earliest sliver of time after the Big Bang, where the cosmos wasn't just governed by quantum rules, it was quantum chaos. At this scale, space-time itself dissolves into what physicists call quantum foam, a frenzied dance of virtual particles and wormholes popping in and out of existence faster than a blink. Think of it like ocean foam on the shore. From a distance, the waves look smooth and unbroken. But up close, you see a churning mess of bubbles, each forming and bursting in an instant. Now replace those bubbles with microscopic universes, each a fleeting quantum fluctuation, and you've got the Planck epoch. In this primordial frenzy, the very concepts of here and now break down. A single point in space could exist in multiple states at once, stretched, twisted, or even tied in knots before snapping back into the foam. Gravity, time, and even causality weren't the steady forces we know today. They were more like suggestions, flickering in and out of relevance as space-time writhed in superposition. This quantum foam wasn't just random noise, it might hold the key to how the universe settled into the reality we recognize. Imagine throwing a handful of dice onto a table. At first, they're all bouncing, spinning, landing on different numbers with every tumble. But given enough time, they'll eventually settle into a fixed configuration. The Planck epoch was like that table in mid-shake, with space-time itself as the dice. Out of that chaos, certain patterns, certain superpositions, could have gained stability, freezing into the laws of physics we observe today. Some theories suggest that dark energy, the mysterious force accelerating the universe's expansion, might be a relic of this quantum turbulence, a faint echo of spacetime's original froth. What's truly mind-bending is that this quantum foam might still exist not just in the distant past but all around us. At scales 1,000,000,000,000 times smaller than an atom, spacetime could still be foaming, with tiny wormholes and black holes blinking in and out of existence. We can't see it because these fluctuations are too brief, too tiny to detect. But if we could peer deep enough, reality might look less like a serene cosmic ocean and more like a boiling quantum storm. The universe isn't just built on the quantum scale, it's still shaking with its energy, a reminder that beneath the calm surface, the wildness of creation never truly ended. What if the universe's first quantum superposition wasn't a natural phenomenon but a glitch in the code? The simulation hypothesis takes the weirdness of quantum mechanics and flips it on its head, suggesting that reality might not be fundamental at all. Instead, it could be a vast, intricate simulation running on some unfathomable quantum computer. Think of it like a video game where the pixels only render when you're looking at them, except here, the pixels are atoms and the player is you. Digital physics takes this idea even further, proposing that the universe isn't just like a computer, it is one. At the smallest scales, spacetime might not be smooth and continuous but pixelated, built from tiny chunks of information like the ones and zeros in a binary code. In this framework, quantum superposition isn't a mystery, it's a feature. It's the universe's way of saving processing power, only calculating the definitive state of a particle when it absolutely has to. So that first cosmic superposition, it might have been the simulation's boot-up sequence, a moment of unresolved code before the program got its bearings. The parallels between quantum mechanics and computing are too striking to ignore. In a quantum computer, qubits exist in multiple states at once, solving problems by exploring every possible solution simultaneously, until they're observed collapsing into a single answer. Sound familiar? It's the same behavior we see in particles at the quantum scale. Some theorists argue this isn't a coincidence. If our reality is a simulation, then its underlying architecture could be built on quantum processing, with superposition acting as the buffer between unrendered possibilities and the stable world we perceive. But here's where things get really interesting. Glitches in the system could explain some of the universe's biggest unsolved puzzles. Dark energy, the force pushing the cosmos apart at an accelerating rate, might not be a physical phenomenon. It could be a memory leak, a sign that the simulation is struggling to keep up with its own calculations. The randomness of quantum events may be just procedural generation, like a video game filling in terrain as you explore. Even the Big Bang itself could be the equivalent of hitting start on a cosmic program, with that initial superposition representing the split-second lag before the code fully loaded. Of course, not everyone buys into this idea. Some physicists argue that simulating an entire universe would require more energy than exists in that universe, a paradox that seems to break the rules. But others counter that if reality is a fractal, nested within deeper layers of existence, then the processing might not happen inside our space but outside it, in a higher dimensional substrate we can't perceive. It's like ants trying to understand the internet. They'd never grasp the concept of servers or code, only the strange behaviors they produce, the most unsettling possibility. If we're living in a simulation, then superposition isn't a bug, it's a design choice, a way to keep the universe running efficiently. And if that's true, then every time you observe something, you're not just seeing reality. You're forcing it to render. What if the universe's first quantum superposition didn't just ripple forward through time, but backward? This is the mind-bending premise of time-symmetric retrocausality, a theory that flips our understanding of cause and effect on its head. At its core is the Wheeler-Feynman absorber theory, a radical idea suggesting that future events can reach back and influence the past, like echoes traveling upstream against the flow of time. Picture a stone dropped into a pond, sending ripples outward, but in this case, the ripples also travel inward, converging back on the stone from the future. The implications for quantum superposition are staggering. If retrocausality is real, then the universe's initial quantum haze might not have been random at all. It could have been sculpted by events that hadn't technically happened yet. Imagine setting up a maze for a mouse, but the mouse's future decisions somehow rearrange the walls of the maze before it even starts running. That's what the Wheeler-Feynman theory proposes. Particles in superposition aren't just undecided, they're actively receiving whispers from their own futures, adjusting their probabilities based on outcomes that haven't occurred. Experiments like the delayed choice quantum eraser give this wild idea some teeth. In these tests, scientists manipulate particles after they've already been measured, and somehow, those later choices appear to rewrite the particle's earlier behavior. It's as if flipping a light switch today could change whether a bulb was on or off yesterday. One famous version of this experiment involves photons passing through a double-slit apparatus. When researchers decide after the fact whether to look at which slit each photon took, their choice seems to retroactively determine whether the photon behaved as a particle or a wave during its initial journey. Critics argue this doesn't prove time is flowing backward, just that quantum systems remain entangled in ways we don't fully grasp. But supporters counter that retrocausality elegantly explains quantum weirdness without invoking multiple universes or conscious observers. If particles can sample their possible futures before committing to a state, it would make superposition less like indecision and more like a cosmic negotiation between past and future. The most thrilling possibility, this could mean the Big Bang itself was shaped by events in our far future. Dark energy's acceleration, the heat death of the universe, even humanity's own observations, might be sending ripples backward to that first quantum flicker, fine-tuning the cosmos into existence. It's a dizzying thought. The universe didn't just unfold from beginning to end. It might have been a conversation across time, with creation whispering to itself from both directions at once. What if the universe's first quantum superposition wasn't random but sculpted by a kind of cosmic natural selection? This is the core of quantum Darwinism, a theory that blends the strangeness of quantum mechanics with the ruthless efficiency of evolution. Picture the early universe as a swirling ocean of possibilities, where countless quantum states flickered in and out of existence. Most were fragile, collapsing almost instantly. But a handful were robust enough to withstand the chaos, imprinting themselves onto the fabric of reality. These weren't just random survivors, they were the quantum equivalents of the fittest, the states best adapted to persist as the universe cooled and expanded. The key to this idea lies in the way quantum systems interact with their environment. In the lab, superposition collapses when particles are observed because the act of measurement forces them to choose a state. But quantum Darwinism flips this around, suggesting that the environment itself acts as a continuous observer, winnowing down possibilities until only the most stable configurations remain. Think of it like a game of musical chairs played by quantum states. Every interaction with the surrounding cosmos kicks out the weaker contenders, leaving behind the ones that can endure. Over time, these survivors become the classical reality we recognize, the familiar rules of physics emerging from the quantum fray. This process might explain one of the biggest mysteries in physics, the quantum to classical transition. Why does the weirdness of superposition fade as objects get larger? A single electron can be in two places at once, but a baseball can't. Quantum Darwinism offers an answer. Larger objects are constantly bombarded by their environment, air molecules, light, even cosmic rays. These relentless interactions measure the system countless times per second, effectively locking it into a single state. The early universe, then, wasn't just a place where quantum rules reigned supreme, it was a battlefield where only the most resilient states could weather the storm of environmental noise and survive long enough to shape the cosmos. Evidence for this might lurk in the cosmic microwave background, the afterglow of the Big Bang. Its faint irregularities could be the fossilized imprints of those early quantum survivors, the states that outcompeted the rest. Even the arrow of time, the fact that entropy always increases, might trace back to this ancient selection process, with the universe's expansion acting like a cosmic sieve, filtering out unstable configurations. The beauty of quantum Darwinism is how it bridges the abstract and the tangible. It doesn't just explain why superposition exists, it shows how the chaos of the quantum world gave birth to the stable, predictable universe we call home. The next time you drop a ball and watch it fall, remember, gravity isn't just a force, it's the legacy of a quantum state that won the universe's first and fiercest competition. Dark energy isn't just some mysterious force pushing the universe apart, it might be the oldest quantum field in existence, a relic from the moment superposition first twisted reality into being. Picture a vast, invisible ocean stretching across the cosmos, its waves not made of water but of pure potential. This is the dark energy quantum field, a seething backdrop of energy so pervasive it makes up nearly 70% of the universe, and its ripples could hold the secret to how everything began. Unlike the cosmic microwave background or the glow of distant stars, this field doesn't shine or scatter. It's quieter than silence, subtler than a shadow. Yet its influence is everywhere, woven into the empty space between galaxies. Quantum field theory suggests that even a perfect vacuum isn't truly empty. It crackles with virtual particles flickering in and out of existence. Dark energy might be the ultimate manifestation of this quantum unrest, a field so finely balanced that its fluctuations could have set the stage for the universe's first superposition. Imagine a calm lake at dawn, its surface so still you could see a single water strider's footsteps. Now replace that lake with the entire cosmos and the ripples with quantum probabilities. That's the scale we're talking about. The cosmological constant problem casts a long shadow over this idea. Einstein originally introduced the constant as a fudge factor to keep the universe static, a decision he later called his greatest blunder. But modern physics resurrected it to explain dark energy's acceleration, only to hit a snag. When theorists calculate how much energy the quantum vacuum should contain, the numbers overshoot observations by a factor of 10 to the power of 120. That's like predicting a teacup could hold all the water in the Pacific Ocean. This staggering mismatch hints that something fundamental is missing in our understanding. Could the answer lie in superposition? Here's where the pieces might fit together. If the early universe existed in a quantum haze, its dark energy field wouldn't have had a single fixed value. Instead, it could have fluctuated across countless possibilities, each with its own cosmological constant. Most of these configurations would have been unstable, collapsing instantly or expanding too violently for matter to form. But a rare few balanced on a knife's edge between chaos and order might have survived long enough to anchor reality as we know it. This isn't just speculation. Some models suggest that dark energy's eerily precise value isn't a coincidence but a consequence of quantum selection, a cosmic Goldilocks scenario where only the just right superpositions endured. Vacuum energy adds another layer to the puzzle. According to quantum mechanics, empty space should brim with energy, a product of particle-antiparticle pairs constantly forming and annihilating. But if that's true, why doesn't this energy overwhelm the cosmos? One provocative answer is that it did once. In the universe's first moments, vacuum energy and dark energy might have been two sides of the same quantum coin, with superposition acting as the exchanger. Picture a gambler placing bets on every possible outcome at once, then cashing in only the winning ticket. The inflationary surge that followed the Big Bang could have been that payout, with the quantum field's fluctuations funneling vacuum energy into the precise, delicate balance we call dark energy today. The implications are profound. If dark energy is indeed a quantum fossil, then its gentle push on the cosmos isn't just shaping our future. It's a whisper from the very first instant of time, a reminder that the universe began not with a single note but with a chord of countless possibilities. And somewhere in the vastness between galaxies, that chord might still be humming, tuning the cosmos one quantum fluctuation at a time. What if the entire universe around you, the stars, the planets, even your own memories, wasn't real, but just a fleeting hallucination of a single, disembodied brain? Welcome to the Boltzmann brain paradox, one of the strangest and most unsettling ideas in modern physics. Named after 19th-century physicist Ludwig Boltzmann, this thought experiment suggests that in an infinite, chaotic cosmos, random quantum fluctuations could spontaneously assemble a fully conscious mind, complete with fabricated memories of an entire lifetime. And if that's true, how could you ever prove you're not one of them? The paradox starts with thermodynamics. Boltzmann realized that entropy, the tendency of systems to descend into disorder, doesn't forbid order from arising spontaneously. It just makes it incredibly unlikely. Given enough time, even the most chaotic systems will stumble into moments of structure purely by chance. In an eternal universe, that means a random jumble of particles could, statistically, arrange themselves into anything: a teacup, a Shakespearean sonnet, or a self-aware brain hallucinating a cosmos. Quantum mechanics amplifies this eerie possibility. If particles can exist in superposition, flitting between states until observed, then a Boltzmann brain wouldn't just be an accident. It could be a quantum accident, existing in multiple configurations until the act of observation locks it into one. But here's where superposition throws a wrench into the theory. For a Boltzmann brain to work, it would need a stable reality to hallucinate, but quantum uncertainty means its own thoughts might never solidify. Imagine trying to solve a math problem while the numbers keep flickering between values. Could a brain built on such shaky foundations ever trust its own conclusions? Some physicists argue this quantum instability undermines the paradox entirely. A Boltzmann brain isn't just improbable, it's fundamentally incoherent, like a mirage that dissolves when you reach for it. Others propose a darker twist. What if our entire universe is the Boltzmann brain's hallucination? In this scenario, the Big Bang wasn't a cosmic beginning but a quantum hiccup, a fleeting moment of order in an otherwise formless void. The galaxies, the laws of physics, even the passage of time would just be artifacts of this single, deluded mind. The idea feels like something from a dystopian sci-fi novel, but it's grounded in cold statistics. Given infinite time and infinite quantum fluctuations, even the most absurd possibilities become inevitable. Yet there's a counterargument hidden in the very physics that spawned the paradox. If the universe is truly infinite, then Boltzmann brains should be vastly outnumbered by stable, long-lasting realities like ours. After all, a fleeting hallucination is infinitely more likely than a 14-billion-year-old cosmos with consistent laws. This statistical tug-of-war leaves cosmologists divided. Some dismiss Boltzmann brains as a philosophical curiosity, while others see them as a warning that our theories of quantum mechanics and cosmology might still be missing something profound. One thing's certain: the paradox forces us to confront the fragility of reality itself. Every observation you make, every memory you trust, could theoretically be the product of a quantum dice roll. But here's the twist: if you're capable of questioning whether you're a Boltzmann brain, you've already stumbled on the best evidence against it. Stable, coherent minds don't emerge from chaos. They're built by billions of years of cosmic evolution, forged in the fires of stars and shaped by the relentless march of entropy. The universe might be stranger than we imagine, but it's almost certainly real, and so are you. What if consciousness isn't just a product of the brain, but a quantum phenomenon woven into the very fabric of the universe? This is the radical claim at the heart of the Penrose-Hameroff or theory, where the mysteries of quantum superposition collide with the inner workings of the human mind. At its core, the theory proposes that the brain's microtubules, tiny protein structures inside neurons, act as quantum processors capable of maintaining superposition states long enough to influence conscious experience. But here's where it gets cosmic. If these quantum vibrations can orchestrate thought, might they also have played a role in orchestrating reality itself? Roger Penrose, the Nobel-winning physicist, and Stuart Hameroff, an anesthesiologist, first proposed this idea by tackling a paradox. How can the brain, a warm, wet, and seemingly chaotic system, exhibit the precision required for consciousness? Classical biology treats the brain as a computer with neurons firing like binary switches, but suggests something far stranger. Inside each neuron, microtubules, hollow tubes made of tubulin proteins, could harbor quantum states, vibrating in superposition until collapsing into a definitive outcome. These collapses, Penrose argues, aren't just random noise. They're moments of non-computable decision-making, where the fuzzy math of quantum mechanics gives rise to the crisp clarity of conscious choice. Now, stretch this idea to the cosmos. If microtubules can harness quantum effects, could the early universe have done the same? Picture the Planck epoch again, that seething quantum foam where space-time itself flickered between possibilities. Or cosmological extension suggests that the universe's first superposition wasn't just a physical event, it was a proto-conscious one. The same quantum vibrations that might underpin human thought could have reverberated through the infant cosmos, guiding the collapse of wave functions into the stable laws we observe today. In this view, the universe didn't just wake up to consciousness, it was born from it, with reality itself as the ultimate act of observation. Critics haven't held back. Many argue that the brain is too warm and noisy for delicate quantum states to survive long enough to matter. Decoherence, the breakdown of superposition due to environmental interference, should, in theory, scramble any quantum effects in neurons almost instantly. Yet Hameroff counters that microtubules might be shielded by their structure or even by biological mechanisms we don't yet understand. Meanwhile, experiments in quantum biology hint that nature might be sneakier than we thought. Photosynthesis, bird migration, and even smell appear to exploit quantum weirdness in ways once deemed impossible for messy living systems. If biology can hack quantum physics, why not consciousness? The debate rages on, but or boldest implication remains. If quantum processes in the brain mirror those at the birth of the cosmos, then consciousness might not be an accident. It could be a cosmic habit, a pattern written into reality from the very first quantum flicker. Whether you find that idea thrilling or outlandish, one thing's certain: it blurs the line between mind and universe in a way that challenges everything we think we know. The next time you pause to reflect, consider this. The act of thinking might not just be happening inside your head. It could be a whisper from the universe's very first thought. To grasp how superposition could be a holographic illusion, we need to venture into the mind-bending territory of string theory's ADS/CFT correspondence, a concept so abstract it redefines where reality truly resides. Picture our three-dimensional universe not as the main event, but as the surface of a far larger, weirder structure. Imagine a soap bubble floating in midair. The fragile film of the bubble represents our cosmos, thin, finite, and seemingly complete unto itself. But the real magic happens inside, in the hidden depths of the bubble's hollow core. In the ADS/CFT framework, our universe is that surface, while the true quantum fireworks unfold in a higher dimensional bulk we can't perceive. Here's where superposition gets turned on its head. Quantum weirdness particles existing in multiple states at once might not be happening within our space at all. Instead, it could be a shadow cast by processes in that higher dimensional bulk. Think of it like watching a puppet show from behind the curtain. The puppet's motions seem mysterious and disconnected until you spot the strings leading upward to the puppeteer's hands. In this analogy, the puppeteer is the bulk, and superposition is just the tangled dance of unseen strings projected onto our lower dimensional stage. This isn't just philosophical musing. The math behind ADS/CFT reveals something astonishing. Every quantum event in our universe could be the holographic reflection of a more fundamental interaction in the bulk. A single particle in superposition here might correspond to a chorus of perfectly ordinary particles in the higher dimensional realm, their combined states weaving the illusion of quantum ambiguity. It's as if a flock of birds, each flying a clear path, could collectively cast a single, flickering shadow that darts unpredictably across the ground. Critics argue this pushes the mystery of superposition into an inaccessible realm, but supporters counter that it resolves a key paradox: why quantum mechanics feels so at odds with gravity. In the bulk, gravity and quantum effects might unite seamlessly, with our universe's disjointed physics merely a flattened echo of that deeper harmony. Some even speculate that black holes, the ultimate quantum gravity laboratories, could be portals where the boundary between bulk and surface frays, letting hints of the higher dimensional truth leak through. The implications are staggering. If ADS/CFT holds, then the universe's first superposition wasn't a property of matter or energy. It was an artifact of projection, a cosmic sleight of hand where higher dimensional certainty masqueraded as lower dimensional uncertainty. Every quantum experiment we conduct, every particle we observe, might not be probing the fundamental layer of reality at all. We could be studying the universe's reflection, like cave dwellers analyzing shadows on the wall, never guessing the vibrant world casting them lies just out of view. Picture the newborn universe not as a smooth, uniform soup, but as a cauldron of seething energy where the fundamental forces were still fused into a single, indistinguishable superforce. In this primordial frenzy, gravity wasn't yet gravity. It was tangled with electromagnetism and the nuclear forces, all vibrating as one. Then, in a flash of cosmic cooling, something extraordinary happened. The forces split apart like oil separating from water, and in that moment gravity emerged as its own entity. This wasn't just a division, it was a quantum phase transition, a shift so profound it might have locked the universe into its first superposition. Phase transitions are all around us, hidden in plain sight. Think of ice melting into water or steam condensing on a mirror. At a specific critical temperature, matter abruptly changes its state, reorganizing itself at the deepest level. The early universe underwent its own version of this, but on a scale we can barely comprehend. As space-time cooled, the unified superforce fractured, and gravity peeled away from the quantum realm. Some theories suggest this separation wasn't clean, it left behind a kind of quantum static, a blurring of states where gravity's grasp on reality hadn't yet solidified. This is where superposition enters the story. In ordinary quantum mechanics, particles can exist in multiple positions or spins until measured. But during the gravity phase transition, the very fabric of spacetime might have flickered between different configurations, like a light bulb stuttering before it settles into a steady glow. The difference, this wasn't just about particles, it was about the stage they stood on. Spacetime itself could have been in superposition, undecided about its own curvature and structure until the transition resolved. Symmetry breaking offers a clue to how this might have played out. In particle physics, symmetries describe the invisible rules that govern how forces behave. When the early universe cooled, these symmetries broke, like a crystal forming from a liquid. The directions it fractures aren't random, they're dictated by underlying quantum probabilities. Gravity's separation could have followed a similar script, with superposition acting as the cosmic dice roll that determined how tightly it would bind the universe. Too strong and reality might have collapsed into black holes instantly. Too weak and matter would never have clumped into galaxies. Instead, we got something in between, a Goldilocks balance that feels suspiciously like a quantum fluctuation frozen into permanence. The echoes of this transition might still haunt the cosmos. Gravitational waves, ripples in space-time from violent cosmic events, could carry faint imprints of that primordial quantum uncertainty. Some models even suggest that dark matter, the invisible scaffold of the universe, might be a relic of gravity's messy divorce from the quantum world, a shadow of the superposition that once ruled everything. What's truly staggering is the scale of this idea. We're not just talking about particles in a lab. This theory implies that the universe's entire gravitational framework, the force that shapes galaxies and bends light, might owe its existence to a quantum coin toss in the first fraction of a second. The next time you feel the tug of Earth's gravity, remember, you're not just standing on a planet, you're standing on a quantum decision made 14 billion years ago, when reality itself was still figuring out what it wanted to be. The universe doesn't have to be a dice game. What if its first quantum superposition wasn't random at all, but guided by an invisible hand? This is the radical promise of pilot wave cosmology, a theory that resurrects an old idea from physicist David Bohm and thrusts it into the cosmic spotlight. While mainstream quantum mechanics treats particles as fuzzy clouds of probability until observed, Bohm's pilot wave theory suggests something far more structured. Every particle has a definite position at all times, steered by a hidden pilot wave that choreographs its motion behind the scenes. Think of a surfer riding a wave. The surfer isn't randomly tossed about but moves with precision, carried by forces deeper than the surface chaos. In Bohmian mechanics, the pilot wave is that unseen force, a cosmic current flowing through spacetime, directing particles along deterministic paths even when they appear to behave probabilistically. Apply this to the early universe and the implications are staggering. The Big Bang's quantum haze might not have been a free-for-all of possibilities, but a symphony conducted by a primordial pilot wave, shaping the collapse of superposition into the orderly cosmos we see today. This stands in stark contrast to the Copenhagen interpretation, quantum mechanics' orthodox framework, which insists superposition collapses are purely random acts with no deeper mechanism. Niels Bohr and Werner Heisenberg famously compared the universe to a cosmic casino where particles choose their states at the moment of observation. No hidden variables, no underlying order. But pilot wave cosmology calls this bluff. If the universe began as a quantum superposition, Bohm's hidden wave could have been the silent architect, ensuring that what looked like randomness was actually a meticulously guided process. Evidence for this might lurk in quantum entanglement, where particles instantaneously influence each other across vast distances. In the Copenhagen view, this spooky action is a brute fact of nature. But Bohm's pilot wave offers an elegant explanation. Entangled particles aren't communicating, they're riding the same underlying wave, like buoys bobbing in sync on a shared ocean current. Scale this up to the birth of the cosmos and the universe's large-scale structure. The way galaxies cluster and void sprawl might not be accidental. It could be the fingerprint of that first universe-spanning pilot wave, a blueprint hidden in plain sight. Critics dismiss pilot wave theory as needlessly complex, adding hidden layers to explain what randomness handles just fine. Yet supporters counter that randomness isn't an explanation, it's a surrender. The Copenhagen interpretation shrugs at the why of quantum behavior, while pilot wave cosmology dares to propose a how. And in an era where we're mapping the cosmic microwave background with unprecedented precision, who's to say we won't find subtle patterns, cosmic ripples too fine-tuned to be mere chance? The debate cuts to the heart of reality itself. Is the universe fundamentally chaotic, a quantum roll of the dice, or is it a cosmic mechanism, its gears turning silently beneath the surface? Pilot wave cosmology doesn't just offer an answer, it reframes the question. The next time you gaze at the night sky, consider this. Those stars might not be the aftermath of quantum randomness. They could be the footsteps of a wave that's been guiding everything since the very beginning. Imagine every particle in the cosmos bound together in a vast, invisible web, not by gravity or electromagnetism, but by an even deeper connection, quantum entanglement. This is the audacious premise of the entangled universe theory, suggesting that the universe didn't just begin with superposition, it began as one. Picture the Big Bang not as an explosion of matter and energy, but as the unraveling of an impossibly dense knot of quantum links, where every atom, every photon, every speck of dust was once intimately tied to everything else. Here's how it might have worked. In the earliest moments of time, the entire universe existed in a single, universal quantum state, a cosmic version of entangled particles in a lab. Just as two electrons can become entangled, their spins mysteriously synchronized across space, the infant cosmos could have been one vast, interconnected system where the state of one particle instantly influenced all others. But then, as the universe expanded and cooled, this grand entanglement began to fray. Tiny quantum fluctuations, amplified by inflation, started pinching off localized regions of spacetime like bubbles forming in boiling water. Each bubble retained some entanglement within itself, but the cosmic web as a whole shattered into fragments. This process, known as decoherence, is what transformed the universe's primordial unity into the patchwork of separate, classical realities we see today. Decoherence isn't just a theoretical curiosity, it's the reason you don't see quantum weirdness in everyday life. In the lab, superposition collapses when particles interact with their environment, as if the universe is constantly taking measurements. In the entangled universe theory, the Big Bang's aftermath was the ultimate decoherence event, with the expanding cosmos acting like an unstoppable wave of measurements, breaking the initial quantum unity. Think of it like a frozen lake cracking under the first rays of spring sunlight. The ice was once a single, rigid sheet, but as temperatures rise, it fractures into countless drifting flows still connected beneath the surface but visibly separate. The echoes of this cosmic disentanglement might still linger. Quantum entanglement leaves subtle fingerprints, correlations between particles that seem too precise to be random. Some physicists speculate that these traces could hide in the cosmic microwave background, the afterglow of the Big Bang. Others suggest that dark matter, the invisible scaffolding of the cosmos, might be a relic of that early entanglement, a shadow of the universe's original quantum cohesion. The implications are staggering. If the universe began entangled, then what we call reality might just be the fragments of a shattered whole. The galaxies, stars, and even your own thoughts could be shards of a single cosmic superposition that once encompassed everything. It's a humbling thought, the separateness we take for granted, the space between you and the screen, the distance between Earth and Alpha Centauri, might be an illusion, a temporary forgetting of the universe's first and deepest connection. What if the Big Bang wasn't the beginning, but the rebound? The white hole quantum echo theory takes the mind-bending idea of a universe born from a black hole's collapse and flips it inside out. Picture a white hole as the opposite of a black hole, not a cosmic vacuum sucking everything in, but a fountain of space-time spewing matter and energy outward. Now imagine that this eruption wasn't random, but a quantum echo from a universe that came before ours. A cosmic ripple bouncing back into existence with all its prior quantum baggage intact. Loop quantum cosmology gives this wild idea some rigor. Unlike classical Big Bang theories, which hit a mathematical wall at the singularity, loop quantum gravity suggests spacetime isn't infinitely divisible, it's woven from tiny, indivisible loops. When gravity becomes too intense, like in a black hole's core, these loops don't collapse into infinity. They bounce. Think of it like compressing a spring to its limit. Instead of breaking, it recoils. In this framework, our universe might not have emerged from nothingness, but from the quantum rebound of a previous cosmos's collapse. Here's where superposition enters the picture. If the prior universe ended in a black hole singularity, its final moments would have been a quantum frenzy, space-time shredded into a storm of overlapping states. When the bounce occurred, that superposition wouldn't just vanish. It would imprint onto the newborn universe like a fingerprint, weaving quantum uncertainty into the fabric of everything we see today. The cosmic microwave background's faint irregularities, they might not just be random fluctuations, they could be quantum whispers from a universe that no longer exists. The implications are dizzying. If white holes are real, they'd be the ultimate time capsules preserving the quantum state of their parent cosmos. Our universe's laws, the strength of gravity, the mass of electrons might not be arbitrary constants but inherited traits, echoes of a previous reality's collapse. Even dark energy, the mysterious force accelerating cosmic expansion, could be a relic of that rebound, like the aftershocks of an earthquake reverberating through space-time. Critics argue there's no observational evidence for white holes yet, but supporters point to tantalizing clues. Certain gamma-ray bursts, the most energetic explosions in the universe, defy conventional explanations. Could they be the dying gasp of a white hole, a final pulse of energy from a rebounding cosmos? Others speculate that the universe's surprising uniformity, the way matter is spread so evenly across vast distances, might not be a coincidence. It could be the result of quantum information smoothing out during the bounce, like a crumpled sheet of paper pressed flat under immense force. The beauty of this theory is how it reframes existence. We're not just stardust, we're quantum dust, remnants of a universe that once was, carrying its superposition like an ancient song. Every atom in your body, every photon streaking through the void, might be part of an echo that's been ringing since before time began. The next time you look up at the night sky, consider this: you're not just seeing stars, you're seeing the aftermath of a cosmic rebound, a universe that refused to die quietly and instead left its quantum signature written across the sky. What if superposition isn't a fact of the universe but a fact about us? This is the provocative stance of quantum Bayesianism, or QBism, a radical reinterpretation of quantum mechanics that flips the script on everything we've covered so far. While most theories treat superposition as an objective feature of reality, particles literally existing in multiple states until observed, QBism argues it's something far more personal, a measure of our own uncertainty. Imagine walking into a pitch-black room with a single light switch. Until you flip it, you can't know if the bulb is burned out or functioning. QBism suggests superposition works the same way. It's not that the particle is in two places at once, but that we lack the information to say definitively where it is. At its core, QBism treats quantum probabilities not as physical properties but as degrees of belief, like betting odds in a cosmic casino. When physicists say an electron is in superposition, they're not describing the electron's state, they're admitting their own ignorance. This might sound like a philosophical quibble, but the implications for cosmology are staggering. If QBism is right, then the universe's first quantum superposition wasn't a primordial condition of reality. It was a reflection of the limits of any observer's knowledge. The Big Bang's quantum haze wouldn't be a physical fog of possibilities, but a representation of how little we or any hypothetical early observer could possibly know about that initial state. Critics pounce on this subjectivity. If superposition is just about belief, why do experiments consistently show interference patterns, the telltale signs of waves overlapping, as if particles really were in multiple states? QBism counters that these patterns emerge from the way quantum systems respond to interaction, not from any intrinsic multiplicity. Think of a magic 8-ball, shake it, and it gives one answer, but the pool of possible answers existed in your head long before you asked. Similarly, the universe's quantum behavior might just be nature's way of answering questions we pose through measurement, not proof of an underlying superposition. Where this gets truly mind-bending is in cosmology. If reality is shaped by observation, as some interpretations claim, does that mean the early universe needed an observer to crystallize its quantum possibilities? QBism sidesteps this by rejecting the idea that observation collapses anything instead. Observations simply update the observer's beliefs. In this view, the universe didn't wait for a conscious mind to pin it down. It just was, with its quantum weirdness reflecting the unavoidably incomplete knowledge any system, even the cosmos itself, could have about its own state. The debate isn't just academic. If QBism holds, it reshapes how we approach cosmic mysteries like dark energy or inflation. These might not be fundamental forces, but artifacts of our limited perspective, like shadows on a cave wall. Conversely, if superposition is objective, then the universe is far stranger than QBism allows. The truth might lie somewhere in between, a reminder that even our boldest theories are, at best, flickering candles in the vast dark of the unknown. One thing's certain: whether superposition is out there in the world or inside our heads, it's still the most tantalizing puzzle in physics. Supersymmetry, one of the most elegant ideas in modern physics, might hold the key to why the universe's first quantum superposition didn't just fade into noise but left a lasting mark on reality. Picture a cosmic mirror where every known particle has a hidden twin, a shadowy doppelganger with properties just different enough to balance the scales of nature. That's the promise of supersymmetry, or SUSY for short, a theory suggesting that in the extreme conditions of the early universe, particles we know and their hypothetical superpartners coexisted in perfect symmetry. But here's the twist: when that symmetry broke, it could have acted like a cosmic freeze ray, locking quantum superpositions into place like bugs trapped in amber. The math behind SUSY is breathtaking in its simplicity. For every fermion, the building blocks of matter like electrons and quarks, there should be a bosonic superpartner. And for every boson, the force carriers like photons and gluons, there's a fermionic twin. In the unimaginable heat of the early cosmos, these particles would have danced in equilibrium, their interactions smoothing out quantum fluctuations like a baker kneading dough. But as the universe cooled, the symmetry shattered, sending superpartners spiraling into invisibility, while ordinary particles froze into the stable states we recognize today. This phase transition wasn't just a minor tweak. It was a cosmic fork in the road, and superposition might have been its secret passenger. Think of it like water crystallizing into ice. As liquid cools, molecules slow down, eventually locking into a rigid lattice. But if you could peer closely at the moment of freezing, you'd catch molecules hesitating between liquid and solid configurations before committing to one. SUSY collapse could have worked similarly on a quantum scale, with particles hovering between states as the symmetry broke, then snapping into fixed roles as the temperature dropped. The difference: instead of water molecules, it was the universe's fundamental building blocks deciding their fate, and those fleeting moments of quantum indecision might still echo in the fabric of spacetime. Evidence for this could lurk in the very particles we've yet to discover. SUSY predicts that while most superpartners became too massive to detect as the universe expanded, some, like the neutralino, might have survived as dark matter. If so, these relics could be more than just invisible cosmic scaffolding. They might be time capsules preserving quantum correlations from the moment of symmetry breaking. Experiments like those at the Large Hadron Collider are hunting for signs of these elusive particles, not just to confirm SUSY, but to peer back into that critical instant when superposition went from a universal condition to a rare quantum curiosity. The implications ripple far beyond particle physics. If SUSY collapse pinned down quantum states, it could explain why the cosmos looks so uniform on large scales. Superposition in the early universe would have created a tapestry of slightly different regions, like patches of fabric cut from the same bolt but dyed in varying shades. As symmetry broke, those variations could have smoothed out, leaving behind the eerily consistent cosmic microwave background we observe today. Even the mysterious imbalance between matter and antimatter might trace back to this moment, with superposition acting as the universe's first and fairest coin toss. Yet Sussy remains tantalizingly out of reach. No superpartners have shown up in colliders, leaving some physicists to wonder if nature took a different path. But absence of proof isn't proof of absence, especially when dealing with energies we can't yet recreate. Whether Sussy is confirmed or not, the core idea stands as a testament to human ingenuity, that the universe's deepest secrets might hinge on symmetries we can barely glimpse, and that the quantum quirks we struggle to explain today could be fossils of a time when reality itself was still deciding what to become. Even empty space is never truly empty. If you could peer into the vacuum between atoms, you'd find a frothing sea of quantum activity, particles and antiparticles flickering into existence for mere instants before annihilating each other. This isn't just theoretical. The Casimir effect proves it. Place two uncharged metal plates incredibly close together in a vacuum, and they'll be pushed together by an invisible force. Why? Because the plates limit the wavelengths of virtual particles that can exist between them, creating a pressure imbalance with the riotous quantum foam outside. Now stretch this phenomenon back to the universe's birth, and you've got a radical idea that these vacuum fluctuations didn't just happen in space but created space itself. Picture the pre-universe as a chaotic quantum foam, with microscopic bubbles of spacetime forming and popping in a frenzy. Normally, these bubbles would vanish as quickly as they appeared. But under the right conditions, perhaps a random fluctuation in the zero-point energy field, one bubble might have resisted collapse. The Casimir effect offers a clue how, if certain quantum wavelengths were suppressed while others amplified, it could have stabilized a tiny region of spacetime, pressing it into existence like a cosmic stamp. This fragile pocket wouldn't just contain superposition, it would be born from it, with every property of the future cosmos existing in a haze of possibilities until decoherence pinned them down. The math gets even wilder when you consider scale. In modern quantum field theory, the vacuum's zero-point energy should be unimaginably dense, enough to curve spacetime into a black hole instantly. Yet we observe a universe that's mostly flat. This discrepancy, known as the cosmological constant problem, might find an answer in those early fluctuations. Imagine a spinning top wobbling violently before settling into smooth rotation. The pre-universe foam could have been that violent wobble, with Casimir-like effects filtering out the most extreme energies, leaving behind just the faint whisper we now call dark energy. Experiments are already chasing shadows of this idea. Scientists measuring forces at nanoscales have found subtle anomalies that could hint at extra dimensions or hidden vacuum properties. And if future probes detect unexpected signatures in the cosmic microwave background, perhaps unexplained patterns in polarization, it might suggest that the universe's first moments were shaped by quantum jitter we're only beginning to grasp. What's truly poetic is how this connects the infinitesimal to the infinite. The same quantum froth that makes tiny plates stick together might have been the sculptor of galaxies, the weaver of spacetime, the silent choreographer of reality's first dance. The next time you stare into the night sky, remember, you're not just looking at stars, you're seeing the aftermath of a quantum shudder so precise it turned chaos into cosmos. What if every instance of quantum superposition, those spooky moments when particles seem to exist in multiple places at once, isn't just a mathematical quirk but a physical tunnel through spacetime itself? This is the breathtaking premise of the ER equals EPR conjecture, a theory so audacious it stitches together two of physics' most enigmatic ideas, wormholes and entanglement. Picture the universe not as a collection of isolated particles, but as a vast, knotted network of microscopic bridges, where every quantum connection is a hidden shortcut through the fabric of reality. The name ER equals EPR is a playful nod to two legendary physics papers. ER refers to Einstein and Rosen, who first theorized wormholes tunnels through spacetime, now called Einstein-Rosen bridges. EPR stands for Einstein, Podolsky, and Rosen, who famously challenged quantum mechanics with their paradox about entangled particles. For decades, these ideas seemed unrelated. But in 2013, physicists Juan Maldacena and Leonard Susskind proposed a radical synthesis. What if entanglement and wormholes are two sides of the same cosmic coin? In this view, when particles become entangled, they're not just mysteriously linked, they're literally connected by quantum-scale wormholes, threads of warped spacetime too tiny to see but fundamental to how the universe operates. Now, stretch this idea back to the universe's first moments. If today's entangled particles are joined by microscopic wormholes, then the early cosmos might have been a seething foam of these connections, a labyrinth of tunnels intertwining every quantum fluctuation. Superposition wouldn't be particles hovering between states, it would be particles existing simultaneously at both ends of a wormhole, like a cosmic game of peekaboo where the same object appears in two places because it's physically threaded between them. Imagine dipping your hand into a pool of water. From the surface, it might look like your fingers are in two places at once, above and below the waterline. In the ER equals EPR framework, superposition works similarly, with the waterline being a wormhole's throat, a hidden corridor through spacetime. This reshapes how we think about quantum weirdness. Take the double-slit experiment where particles behave as waves, creating interference patterns as if they pass through both slits simultaneously. If ER equals EPR holds, the particle isn't magically splitting. It's traversing a wormhole that branches to both slits, its journey through spacetime folding like an origami maze. Even entanglement's spooky action at a distance gets demystified. Particles aren't communicating faster than light. They're simply taking a wormhole shortcut, like ants crossing a leaf by crawling through its veins instead of along its edges. The implications for cosmology are staggering. If spacetime is woven from this quantum wormhole network, then the universe's first superposition might have been less like a fog of possibilities and more like a cosmic subway system under construction, with tunnels linking every point to every other point in a tangled web. As the universe expanded, some of those wormholes would have stretched and snapped, leaving behind the frayed connections we now call entanglement. Others might have stabilized, becoming the gravitational scaffolding for galaxies and black holes. Critics argue that ER equals EPR remains speculative, lacking direct experimental proof, but supporters counter that it's too elegant to ignore, a bridge between quantum mechanics and general relativity that could finally unite these clashing theories. Future experiments, like measuring the quantum properties of spacetime itself or probing the interiors of black holes, might one day test this idea. Until then, it stands as a tantalizing reminder. The universe's deepest secrets might not lie in particles or forces, but in the hidden highways connecting them, a cosmic labyrinth where every quantum mystery is just a doorway waiting to be opened. The universe might not be smooth and continuous at its core. What if spacetime itself is stitched together from tiny, discrete chunks like a cosmic quilt? This is the radical vision of the quantum gravity model, where the fabric of reality isn't woven from seamless threads but built from interconnected nodes, a vast network of quantum links that define both space and time. Picture the internet, a sprawling web of servers and cables where information hops from point to point rather than flowing like water. Now imagine spacetime operating the same way, with every point in the universe connected to its neighbors not by smooth geometry, but by quantum bonds that flicker between existence and nothingness. In this framework, superposition isn't just something particles do. It's baked into the very structure of reality, a natural consequence of spacetime's pixelated origins. The quantum gravity model shares striking parallels with loop quantum gravity spin networks, where spacetime emerges from braided strands of quantized gravity. But while spin networks focus on the gravitational field's granularity, quantum gravity takes a broader view. Here, the universe starts as a featureless soup of interconnected nodes, a cosmic proto-network where every connection is equally probable. As the cosmos cools, some of these links strengthen, crystallizing into the dimensions we recognize: up, down, left, right, past, future, while others fade into irrelevance. Superposition in this model isn't a bug, it's a relic of that primordial indecision, a hesitation in the network's wiring that never fully resolved. To grasp how this works, think of ice forming on a lake. Above freezing, water molecules move freely, their connections transient and chaotic. But as temperatures drop, they lock into a rigid lattice, trading fluidity for structure. Quantum gravity proposes a similar phase transition for spacetime itself. In the searing heat of the early universe, every node was connected to every other node, a buzzing hive of potential geometries. As the cosmos expanded and cooled, those connections froze into a stable pattern, but not perfectly. Residual quantum fluctuations left some links in a state of ambiguity, creating regions where spacetime itself exists in superposition, unable to decide between competing configurations. These flickering connections could explain some of quantum mechanics' deepest puzzles. Take entanglement. If two particles are tied by a surviving primordial link, a thread of the original, all-connected network, their instantaneous correlation stops being spooky and starts making topological sense. Even the speed of light, the universe's ultimate speed limit, might emerge from how quickly information can hop between nodes in the graph, like a rumor passing through a crowd, one whisper at a time. Critics argue that quantum gravity's abstract math makes it hard to test, but supporters point to subtle signatures it might leave in the cosmos. If spacetime has a granular structure, ultra-high-energy cosmic rays, particles traveling from distant galaxies should stumble over that graininess like a sprinting athlete hitting a patch of sand. Some experiments hunting for these stutters in particle arrival times have found anomalous results, though the evidence remains inconclusive. Others speculate that quantum gravity's imprint might hide in the cosmic microwave background's polarization patterns, a faint fossil of spacetime's first shaky steps toward coherence. What's truly revolutionary about this idea is how it reframes existence. We're used to thinking of space as a passive stage and particles as actors upon it. But in quantum gravity, the stage and the actors are made of the same stuff, a dynamic, evolving network where geometry and quantum behavior arise from the same deeper game of connections. The next time you glance at the night sky, consider this. The vast distances between stars might not be empty stretches of nothingness, but the visible traces of a cosmic decision made long ago, when spacetime itself chose which links to keep and which to sever, leaving behind the ghostly echoes of superposition as its unfinished business. Time might not be a fundamental feature of the universe. What if it's just an illusion, a side effect of quantum systems chasing equilibrium? This is the startling premise of the thermal time hypothesis, a theory that rewrites the origin of time itself as a thermodynamic mirage. Forget clocks ticking or celestial motions marking the hours. According to mathematician Elaine Kahns, time emerges from the chaotic dance of particles seeking balance, a cosmic game of hot and cold where superposition plays the referee. Imagine a cup of coffee left on a counter. At first, steam rises in swirling tendrils, the liquid's heat fighting against the room's cooler air, but slowly, inevitably, the two temperatures equalize. The thermal time hypothesis suggests reality works the same way, not with coffee and air, but with quantum states trading energy until they reach equilibrium, and the flow of time is just our way of experiencing that relentless march toward balance. At the quantum level, particles don't experience time as we do. Instead, they exist in a web of probabilities, their states entangled in a timeless superposition. Kahn's breakthrough was realizing that what we perceive as time's arrow, the unstoppable drift from past to future, could be a statistical illusion. Just as a deck of shuffled cards tends toward disorder, quantum systems evolve toward thermal equilibrium, and our perception of time might simply be the brain's way of tracking that progression. In this view, the universe's first superposition wasn't frozen in time. It was outside of time entirely, a soup of possibilities waiting for thermodynamics to impose order. Statistical mechanics offers a clue to how this works. In a gas chamber, trillions of molecules collide randomly, yet their collective behavior follows predictable rules: pressure, temperature, entropy. The thermal time hypothesis applies this logic to spacetime itself. Just as molecular chaos gives rise to the smooth averages we call thermodynamics, quantum chaos might give rise to the smooth illusion we call time. Picture flipping through a flipbook. Each page is static, but move them fast enough and the images seem to flow. The universe could be that flipbook, with each page a quantum configuration, and time the blur our brains stitch together as the system evolves. The implications for superposition are profound. If time isn't fundamental, then quantum particles don't hover between states. They simply exist in all possible states until thermodynamics forces a choice. This reshapes the double-slit experiment's mystery. Particles aren't splitting into parallel timelines. They're trapped in a pre-time limbo where every path is equally real until thermodynamic gradients break the symmetry. Even the Big Bang's fiery dawn might need rethinking. Instead of a temporal beginning, it could mark the moment quantum fluctuations first tipped out of equilibrium, birthing time as a byproduct of their quest for balance. Critics argue this reduces time to a hallucination, stripping it of physical reality. But supporters counter that thermodynamics already governs so much of physics. Why not time itself? Future experiments measuring quantum systems near absolute zero, where thermal noise fades, might test the idea. If time's flow weakens as temperatures drop, it could hint at thermodynamics' hidden role. One thing's certain: if the thermal time hypothesis holds, then superposition isn't just a quantum quirk. It's a glimpse of a deeper, timeless reality, where the universe's first moments weren't ticking forward but tumbling toward the illusion we now call now. Could the act of observation be more than just a passive peek at reality? Could it be the very force that jump-started the cosmos? This is the startling premise of the observer-induced cosmic inflation theory, which suggests the universe's explosive expansion wasn't a random event but a quantum reaction to being seen. Picture a shy performer waiting in the wings until the spotlight hits, and suddenly they burst into motion. In this radical framework, the Big Bang's inflationary surge was that moment of activation, sparked by some primordial act of attention that pinned the universe's quantum haze into a definite reality. The roots of this idea stretch back to physicist John Wheeler's participatory universe principle, where he famously declared that reality emerges from acts of observation, like a game of 20 questions where the answers shape the questions themselves. Apply this to cosmology, and the implications are staggering. The universe didn't inflate because of some abstract quantum field. It inflated because something or someone was looking. But here's the twist: this observer wouldn't need to be human or even conscious. In quantum physics, an observation is any interaction that forces a system to choose a state, whether it's a photon hitting a detector or a stray atom bumping into another. So the first observer might have been as mundane as a quantum fluctuation glancing off another, collapsing probabilities into certainty and setting off a chain reaction that ballooned spacetime itself. This reshapes how we think about inflation's famous fine-tuning problem. The universe's expansion had to be exquisitely calibrated. Too fast, and matter would never clump into galaxies. Too slow, and everything would collapse back into a black hole. Traditional theories struggle to explain this razor's edge precision, but observer-induced inflation offers an elegant solution. If the act of measurement nudged the universe out of superposition, then its expansion wasn't arbitrary. It was the inevitable outcome of quantum probabilities resolving into a stable state. Think of it like shaking a snow globe. The swirling chaos inside only settles when you set it down, and the way the flakes land isn't random but dictated by the globe's structure and your hand's motion. Similarly, the universe's parameters might be the printout of an ancient quantum observation, with inflation as the moment the cosmic dice stopped rolling. Evidence for this might hide in the universe's large-scale structure. If observation seeded inflation, then the distribution of galaxies could bear the imprint of that first quantum interaction, like ripples frozen in time from a pebble tossed into a pond. Intriguingly, certain anomalies in the cosmic microwave background, like the controversial axis of evil pattern, show alignments that defy standard inflationary predictions. Could these be scars from an observer-driven trigger? Even dark energy's mysterious push could fit this model, not as a new force, but as the universe's lingering awareness of being measured, a quantum memory etched into spacetime. Critics argue this veers dangerously close to anthropocentrism, putting consciousness at the center of physics. But proponents counter that it's not about human observers, it's about the universality of quantum interaction. Every particle, every collision, every exchange of energy is a kind of observation, weaving reality through an endless web of mutual measurement. In this view, the cosmos isn't a pre-written script but a live performance, unfolding only because its actors are also its audience, a hall of mirrors where the first glance broke the silence and set the stars alight. What if the universe's most fundamental properties, mass, spin, even causality, could detach from reality like the grin of the Cheshire Cat? In quantum physics, the Cheshire Cat effect describes a particle whose properties, like polarization or charge, can seemingly separate from the particle itself, leaving behind a ghostly imprint of attributes without substance. Now stretch this concept to cosmic scales, and you've got the quantum Cheshire Cat universe, a theory proposing that the newborn cosmos didn't just exist in superposition, but that its very identity flickered between states with properties like mass and energy hovering independently of the spacetime they were meant to define. Picture the early universe as a cosmic magic show where the rabbit isn't just hidden in the hat itself is an illusion. In ordinary quantum mechanics, particles can be in two places at once. But in a Cheshire Cat scenario, a particle's location might stay fixed while its mass drifts elsewhere, like a shadow untethered from its owner. Apply this to the Big Bang and the implications are dizzying. The universe's first moments might not have been a clean assembly of matter and energy, but a surreal carnival where gravity existed without mass, or light without photons, or even time without change. It's as if the cosmos was trying on different costumes, mixing and matching properties until the act of observation or some primordial quantum interaction forced it to commit. The math behind this isn't pure fantasy. Experiments have already demonstrated Cheshire Cat effects in labs. In one groundbreaking study, neutrons passed through a beam splitter, but their magnetic properties took a different path, as if the particles' spin decided to go sightseeing while the neutrons themselves marched straight ahead. Scale this up to cosmology, and you're left with a provocative question. Could the universe's spin or mass have once wandered freely, imprinting faint echoes of their journey into the fabric of spacetime? Some theorists speculate that dark matter, the invisible stuff outweighing visible matter 5-1, might be a cosmic Cheshire grin, the detached mass of an early universe still lingering where it doesn't quite belong. Critics argue this stretches metaphor too far, but supporters point to oddities in the cosmic microwave background regions where temperature fluctuations don't align with matter distribution, as if the universe's properties got lost on their way home. Others suggest that quantum entanglement, with its eerie synchronicity across distances, might be a relic of this early detachment, a reminder of a time when properties weren't tied to objects but floated like untethered balloons. The beauty of this idea lies in its defiance of intuition. We're used to thinking of the universe as a collection of things with fixed traits, but the quantum Cheshire Cat universe whispers a different story, that reality's foundations might be less like a rock and more like a rumor, a fleeting arrangement of attributes that only seem solid because we're here to pin them down. So the next time you feel the weight of your body or watch the steady tick of a clock, consider this: those sensations might not be universal truths. They could just be the costume the cosmos chose to wear today. What if the universe's first quantum superposition wasn't a feature of reality, but a flaw in its fabric? Imagine spacetime not as a smooth canvas but as a tapestry woven from intricate knots, where a single twisted thread could unravel the whole design. This is the essence of the topological quantum field origin theory, which frames superposition as a cosmic defect, a snag in the primordial weave of existence. Think of it like a crack in ice, seemingly insignificant, yet capable of redirecting entire glaciers. At the birth of the cosmos, such a quantum crack might have split reality into overlapping possibilities, leaving behind a universe that couldn't quite decide what it wanted to be. Knot theory offers a mesmerizing way to visualize this. In mathematics, knots aren't just tangled shoelaces, they're closed loops with intricate, non-repeating patterns. When two knots intertwine, they create new structures called braids, which can encode quantum information. Now picture the early universe as a seething plasma of these knotted fields, their braids tightening and loosening in the fiery chaos. A single misaligned twist, a topological defect, could have birthed superposition, forcing the cosmos to exist in multiple braided configurations simultaneously. It's as if the universe tried to tie its shoes while wearing mittens, fumbling the knot into a quantum limbo where every possible tangle coexisted. Real-world analogs like Enyon quasiparticles make this even wilder. In certain ultra-cold materials, electrons don't behave like individual particles, they merge into collective excitations called enyons, which remember how they've braided around each other even when separated. These exotic states are more than lab curiosities, they're proof that topology can dictate quantum behavior. Scale this up to cosmology, and the early universe's superposition might have been a kind of cosmic enyon, a defect in spacetime's weave that preserved multiple histories until decoherence forced a choice. The implications ripple through modern physics. If superposition is topological, it could explain why quantum states are so resilient to noise. Their knots resist unraveling. Dark matter's elusive nature might even fit this model. Perhaps it's not a particle at all, but a shadow of those primordial defects, ghostly knots left dangling when the rest of reality smoothed out. Even Entanglement's spooky links could be reinterpreted as distant strands of the same cosmic braid, their connection written into spacetime's DNA. Critics argue that scaling up enyon physics to the universe strains plausibility, but supporters point to anomalies in the cosmic microwave background, strange cold spots and asymmetries that defy conventional explanations. Could these be the scars of ancient topological tears? Future quantum computers, which exploit enyon braiding for error-resistant calculations, might inadvertently test this idea. If they succeed, it would hint that the universe itself runs on similar rules, with superposition as its original programming glitch. The beauty of this theory lies in its inversion of perspective. We're accustomed to thinking of quantum weirdness as something added to reality, a layer of complexity atop classical physics, but topology suggests the opposite. Superposition isn't an extra feature. It's the universe's way of patching over its deepest flaws, a cosmic workaround for a spacetime that couldn't quite tie itself together cleanly. The next time you marvel at the night sky, remember, those stars might not just be balls of gas. They could be stitches in a quantum quilt holding together a reality that's still trying to mend its first frayed edges. Black holes aren't just cosmic vacuum cleaners. They might be the universe's ultimate quantum archivists. The quantum Darwinism of black holes theory takes the mind-bending idea that quantum states evolve through environmental selection and scales it up to the most extreme objects in existence. Picture a black hole's event horizon not as a one-way door to oblivion, but as a cosmic sieve, filtering quantum superpositions until only the most stable configurations survive. Just as biological Darwinism shapes life through natural selection, this framework suggests black holes could have sculpted reality itself by fixing the early universe's quantum uncertainties into permanent cosmic blueprints. The connection to the black hole information paradox is where things get truly fascinating. For decades, physicists have wrestled with a glaring contradiction. According to quantum mechanics, information can never be destroyed, yet black holes appear to erase it completely when matter crosses their event horizons. The paradox implies our understanding of physics is incomplete, but what if the solution lies in how black holes process superposition? Imagine throwing a library into a furnace. The books burn, but if every ash particle retained a scrambled imprint of the text, the information wouldn't truly be lost, just transformed. Black holes might work similarly, with their intense gravity acting like a quantum printer, encoding the properties of swallowed particles onto their event horizons in a process called holographic storage. This reshapes how we view the early universe's quantum haze. If primordial black holes existed in the first moments after the Big Bang, as some theories suggest, they could have acted as cosmic stabilizers. As vast numbers of quantum fluctuations bubbled in the seething plasma of the young cosmos, black holes would have absorbed some of these superpositions, effectively measuring them by locking their states onto event horizons. Like a photograph freezing a dancer mid-motion, this process might have pinned down quantum uncertainties that otherwise would have flickered indefinitely. The resulting imprint, a faint holographic record of the universe's first quantum choices, could still linger in the Hawking radiation slowly leaking from ancient black holes. Stephen Hawking's groundbreaking work on black hole radiation plays a pivotal role here. His calculations showed that black holes aren't truly black. They emit energy evaporating over unimaginable timescales. But if information really is preserved on the event horizon, then this radiation isn't random noise. It's a slow-motion broadcast of the quantum day to the black hole absorbed, a cosmic message in a bottle tossed into the future. Applied to the early universe, this means the first superpositions didn't just fade into the background. They were etched into the fabric of reality by black holes, their quantum states preserved like insects in amber until decoherence cemented them into the laws we observe today. The implications ripple through modern physics. If black holes fixed early superpositions through quantum Darwinism, it could explain why our universe appears so finely tuned for complexity. Random quantum fluctuations would have produced a chaotic cosmos, but selective preservation by black holes might have filtered out unstable configurations, leaving behind only the self-consistent patterns that allowed galaxies, stars, and life to emerge. This isn't just about the past, it suggests that black holes are still shaping reality today. Every time one swallows matter, it's not destroying information but curating it, pruning the quantum multiverse's infinite possibilities into a single, coherent timeline. Critics argue this stretches the math beyond what's testable, but supporters point to tantalizing clues. The holographic principle, the idea that all information within a volume of space can be encoded on its boundary, gains new weight if black holes are cosmic librarians. Even dark energy's mysterious acceleration could fit this model, as the cumulative effect of countless black holes subtly adjusting spacetime's quantum fabric. Future gravitational wave detectors might uncover more evidence, searching for anomalies in black hole mergers that reveal how information is preserved. The beauty of this theory is how it turns a paradox into a creative force. Black holes aren't just devourers of light. They might be the universe's original editors, scrubbing quantum noise until only the clearest signals remained. Every atom in your body, every photon streaking through the void, could owe its existence to these cosmic gatekeepers, who didn't just witness the birth of reality but helped write its first and most enduring draft. Deep in the tunnels of the GEO 600 gravitational wave detector, scientists stumbled upon something unexpected, not the ripples of colliding black holes they were hunting, but a persistent, whisper-thin static crackling at the very edge of their instruments. Dubbed holographic noise, this anomalous signal might be more than just technical interference. It could be the faint echo of the universe's first quantum superposition, a remnant of spacetime's primordial pixelation imprinted on reality like a watermark. The holographic principle suggests that all the information in our three-dimensional universe might be encoded on a two-dimensional surface at its boundary, like a DVD storing a movie. If true, spacetime itself would have a fundamental graininess, a pixel-like structure at the Planck scale. These quantum pixels wouldn't be static. They'd flicker as the universe continuously updates its holographic projection, creating a subtle background noise. That's what the GEO 600 team may have detected, the universe's quantum fuzziness bleeding into the macroscopic world. At first glance, the idea sounds absurd. How could a gravitational wave observatory pick up something so infinitesimally small? The answer lies in the detector's extraordinary sensitivity. GEO 600 uses laser interferometry to measure distortions in spacetime smaller than an atom. But in 2008, researchers noticed an unexpected noise floor that couldn't be explained by thermal fluctuations or mechanical vibrations. Intriguingly, this noise matched predictions made by physicist Craig Hogan, who theorized that holographic graininess would manifest as jitter in the positions of the detector's mirrors, as if spacetime itself were vibrating like a drumhead at the quantum scale. Imagine trying to watch a high-definition movie projected onto a screen made of coarse sand. No matter how sharp the image, the grain of the sand would create a faint shimmer. Similarly, if spacetime is fundamentally pixelated, then even the most precise measurements would eventually hit a limit, a blur caused by the universe's underlying quantum structure. The GEO 600 anomalies could be that blur, the first experimental hint that reality isn't perfectly smooth but built from discrete, fluctuating bits. Critics argue that the signal might still be mundane, perhaps an undiscovered source of instrumental noise or an artifact of the laser system. But supporters counter that the noise's frequency spectrum aligns eerily well with holographic predictions. Future detectors like LISA, which will operate in the quiet of space, could settle the debate. If they confirm the noise, it would revolutionize our understanding of quantum gravity, proving that superposition isn't just a property of particles, it's woven into the fabric of spacetime itself. What's truly tantalizing is the cosmic connection. If holographic noise is real, then GEO 600 might not just be detecting quantum graininess, it could be hearing the universe's first moments reheating themselves. During the Big Bang, spacetime would have been a seething quantum foam with every point in superposition. As the cosmos expanded and cooled, most of those fluctuations smoothed out, but some might have frozen into the holographic noise we see today. A cosmic fossil of superpositions reign over reality. Think of it like an old vinyl record. The crackles and pops aren't flaws in the music, they're artifacts of the record's physical structure, reminders of how the sound was stored. Similarly, holographic noise wouldn't be a glitch in spacetime but a feature, a whisper from the universe's quantum origins. Every detector hunting for gravitational waves might already be swimming in this signal, mistaking it for background static when it's actually the soundtrack of creation, a reminder that reality, at its core, is still deciding what it wants to be. Long before particle colliders or quantum equations, Humanity told stories that captured a truth science is only now uncovering that reality at its core thrives on duality. The ancient Chinese concept of yin and yang, with its swirling dance of opposites, doesn't just depict balance, it mirrors quantum superposition's essence, where particles exist in states of both this and that until pinned down by observation. Consider the Norse myth of Odin, who sacrificed an eye to drink from the well of wisdom, embodying the paradox of gaining clarity by embracing ambiguity. Or the Hindu god Shiva, simultaneously destroyer and creator, his cosmic dance a metaphor for the universe's flickering between possibilities. These aren't mere coincidences, they're echoes of an intuitive grasp of quantum logic, etched into mythology millennia before Schrödinger's cat entered the conversation. Take the Greek legend of Janus, the two-faced god guarding doorways. His dual visage symbolized transitions past and future, inside and outside, but it also resonates with the quantum notion that reality exists in a liminal space until measured. Indigenous Australian Dreamtime stories speak of a time before time where the world was unformed, a shimmering potentiality not unlike the quantum foam theorized by physicists. Even the biblical account of creation, "Let there be light," could be read as a collapse of superposition, where the undefined void crystallizes into ordered reality through divine observation. Skeptics dismiss these parallels as retroactive pattern matching, arguing that ancient cultures lacked the tools to conceptualize quantum mechanics. But proponents counter that intuition often precedes proof, just as Democritus theorized atoms centuries before microscopes revealed them. The Vedas, Hindu scriptures dating back over 3,000 years, describe a universe where nothing is lost, only transformed, a startling precursor to quantum field theory's conservation of information. Similarly, Taoist texts speak of the uncarved block, a state of pure potential that mirrors the unobserved quantum wave function. Perhaps the most compelling link lies in alchemy's quest to unite opposites, Mercury's fluidity and sulfur's solidity, into a perfected whole. Modern quantum chemistry reveals that electrons don't orbit nuclei like planets but exist as probability clouds, their positions smeared across space until interaction forces a choice. This blurring of boundaries was precisely what alchemists sought to harness, their symbolism a coded language for quantum entanglement avant la lettre. The debate isn't about whether ancient mystics understood wave functions, it's about the persistence of certain archetypes across cultures. From Egyptian mats feather balancing truth against lies to Celtic knots endlessly looping without beginning or end, these symbols suggest a deep-seated human recognition that reality is woven from contradictions. Quantum physics, with its particles that are also waves and cats simultaneously alive and dead, might not be overturning intuition so much as vindicating it, proving that the myths weren't wrong, just poetic. As we stand at the crossroads of science and spirituality, these narratives remind us that the universe has always whispered its secrets in metaphor. The next time you gaze at a yin-yang symbol, consider this. That ancient artists might have painted the first quantum equation, capturing in brushstrokes what would take physicists centuries to express in mathematics. Reality, it seems, has always been stranger than fiction, and our ancestors, in their way, knew it all along. From the seething quantum foam of the Planck epoch to the holographic whispers echoing through space-time, we've journeyed through a labyrinth of theories that rewrite the cosmic origin story. Each one flips reality on its head in its own way, whether painting the Big Bang as a quantum fluctuation in an endless void, a collision of parallel worlds, or even a simulation booting up in some higher dimensional computer. The sheer diversity of ideas is staggering. Some treat superposition as a cosmic accident, others as the universe's foundational language, and a few dare to suggest it's all a mirage projected from the edges of existence. Yet beneath the wild variations lies a shared truth: reality is far more fluid, more interconnected, and more mysterious than our everyday experience suggests. Take the holographic principle, which reduces our 3D universe to a flat cosmic movie screen, or the entangled universe theory, where every particle remembers its primordial kinship with all others. Then there's pilot wave cosmology, where hidden currents guide quantum randomness like an invisible hand, and quantum gravity, where space-time itself is a patchwork of flickering nodes. Even consciousness gets a starring role in some theories, weaving the fabric of reality through observation. The debates between these ideas aren't just academic, they're a battleground for the soul of physics, where the stakes are nothing less than understanding why anything exists at all. What's exhilarating is how these theories refuse to sit still. They evolve, collide, and spawn new hybrids, much like the quantum phenomena they seek to explain. Some may eventually fall to evidence, while others could rise to reshape science itself. But their collective power lies in the questions they force us to confront. Is the universe a solitary accident or one bubble in an infinite multiverse? Are we passive observers or active participants in creation? And if quantum weirdness underpins everything, what does that say about the nature of existence itself? Now it's your turn. Which of these mind-bending visions feels closest to the truth? Do you see reality as a cosmic hologram, a quantum network, or something even stranger? Drop your thoughts in the comments, and if you're hungry for more deep dives into the universe's greatest mysteries, hit that subscribe button. The quantum conversation is just getting started, and the next breakthrough could be a click away. Until then, keep looking up and questioning everything. The universe's secrets